the Altiplano in Chile. Few landscapes on Earth offer more spectacular views, with emerald green, high-altitude lakes amid stretches of land shining in the colors of rich mineral deposits. The background is formed by majestic volcanoes. The air is crisp and crystal clear. San Pedro de Atacama, a picturesque Chilean village on the border between Chile, Argentina and Bolivia. From here, a winding road leads to Paso de Jama and Argentina, crossing the 5,000-meter elevation mark. As vehicles climb the road towards the mountain pass, their engines struggling in the thin air, travelers are exposed to a landscape of serene beauty. Higher up, beyond 5,500 meters, you might expect to see snow-capped mountains. But this is not snow. It is sulfur. This is Magic Land. And soon it will become the site of a unique science project to study deep space, and thus to learn about the earliest epochs of the universe, billions of years before the Earth was formed. This will be the site for the Atacama Large Millimeter Array. For centuries, astronomers have studied the stars. Without the possibility to travel to the stars, collecting and analyzing the light emitted by them was the only way to extract information about those celestial objects. In 1931, Karl Jansky, while investigating the sources of static that might interfere with transatlantic shortwave radio voice transmissions, made a stunning discovery. Radio emission was coming from the cosmos. Jansky's discovery pushed wide open a new window on the universe for astronomers, allowing them to study the sky not only in visible light but also at radio wavelengths. Radio astronomy, as the new branch was called, led to the realization of the ubiquity of hydrogen, the most abundant element in the universe, and to the discovery of exotic objects such as quasars, now known to reside in the centers of many galaxies, and pulsars, those enigmatic residues of supernovae representing some of the most dramatic events that happen in the universe. In the second half of the century, radio astronomy was joined by X-ray and gamma-ray astronomy, relying on space-borne observatories, and also by a new branch known to astronomers as millimeter astronomy. In technical terms, millimeter astronomy covers electromagnetic radiation between infrared light and classical radio frequencies. Millimeter astronomy has been called the astronomy of the cold universe. Galaxies, stars and planets form in cold regions, that is, in environments of about 10 degrees above absolute zero. At this temperature, they're not easily detectable in other wavebands. Millimeter radiation penetrates the dense clouds of dust where stars are born, enabling astronomers to examine in detail the processes of star and planet formation. With millimeter antennas, it is also possible to study the earliest and most distant galaxies, when the first light in the universe was emitted. More than anything else, therefore, millimeter astronomy is the study of origins. Millimeter telescopes have primarily been located in the United States of America, in Europe and in Japan. Some facilities with several telescopes working together in arrays. At the La Silla Observatory in Chile, operated by ESO, the European Astronomy Organization, the 15-meter Swedish ESO CEST telescope was for a long time the only antenna of its kind in the southern hemisphere. But now, astronomers are building the world's most powerful facility for millimeter astronomy, a giant array of antennas. It will be constructed at 5,000 meters elevation on the plateau of Chajnantor in the Chilean Altiplano, the highest permanent astronomical observing site in the world. Known by the acronym of ALMA, the array will be composed of 64 12-meter sub-millimeter quality antennas. They will work together, functioning as a single giant antenna. The baselines will extend up to 16 kilometers to make high-resolution images. Its superconducting receivers will be cryogenically cooled to less than 4 degrees above absolute zero, and will cover the frequency range from 30 to 950 gigahertz. The signals will be digitized and transmitted to a central processing facility, where they're combined and processed at terabit data rates. The total collecting surface will exceed 7,000 square meters, larger than a football field, making ALMA more than 50 times more sensitive than any existing telescope array in the world. The shape of each antenna must remain extremely precise under all conditions. The overall accuracy over the entire surface of one antenna, 12 meters in diameter, must be better than 25 micrometers, 1/3 of the diameter of a human hair. The combination of large collecting area and such high precision results in extremely high sensitivity, allowing the detection and measurement of radiation even from the faintest and most distant objects. The individual antennas, each weighing more than 70 tons, are movable, allowing for changing the configuration of the array. In the most compact configuration, the sensitivity of ALMA is maximized to detect extremely faint objects, while the so-called zoom spiral array allows observations with continuously variable spatial resolution or sharpness. The Atacama Large Millimeter Array, ALMA, is an international astronomy facility. ALMA is an equal partnership between Europe and North America, in cooperation with the Republic of Chile, and is funded in North America by the U.S. National Science Foundation, NSF, in cooperation with the National Research Council of Canada, NRC, and in Europe by the European Southern Observatory, ESO, and Spain. ALMA construction and operations are led on behalf of North America by the National Radio Astronomy Observatory, NRAO, which is managed by Associated Universities Incorporated, AUI, and on behalf of Europe by ESO. Furthermore, Japan is expected to join the project, turning it into the first truly global astronomy project in the world. The scientific goals and the very large size of ALMA require the application of state-of-the-art technology. The challenges of engineering the unique ALMA telescope begin with the need for the telescope to operate in the extreme conditions high up in the Earth's atmosphere, where the radiation at millimeter and sub-millimeter wavelengths from cosmic sources penetrates to the ground. The technological challenges posed by ALMA are very diverse and include the use of composite materials for accurate reflector antennas, the development of precise metrology systems, receivers for sub-millimeter wavelengths, photonic signal transportation and manipulation, very high-speed digital electronics, and development of software systems for remote control of the telescope, data handling and analysis. To test new design concepts, the ALMA partners have decided to build prototype antennas. The prototypes must meet identical specifications, but feature very different designs. This approach ensures that the best possible technologies are incorporated into the final production antennas. In North America, Vertex RSI was selected by AUI for construction of a prototype antenna, while ESO chose a consortium of European Industrial Engineering of Italy and Alcatel Space of France for the production of another prototype. Here, the European prototype is shipped on board a giant Airbus Beluga cargo plane to a test site near Socorro, New Mexico. Here, at a site operated by the NRAO and home of the very large array of radio telescopes, the ALMA prototypes are assembled and subjected to thorough testing before selection of the design concept which will finally be used for the full array. For several months, the performance of the prototypes will be monitored by a joint European-North American team of experts. The specific design solutions will reveal their individual strengths and weaknesses in terms of technical and scientific performance under real-life conditions and operations. In addition to the EIE Alcatel antenna and the Vertex antenna, a third antenna, built by Mitsubishi Electric for the National Astronomical Observatory of Japan, is also being tested. Meanwhile, preparations for developing the site at Chajnantor in Chile are underway. Already for many years, specialists from Europe, the United States and Japan have carried out detailed site testing activities. These tests have focused on the meteorological conditions as well as the observation conditions at radio wavelengths. The tests included launches of balloon-borne radio probes to measure the atmospheric conditions as well as monitoring of variations in water vapor density in the atmosphere by means of interferometers, of crucial importance to observations in the millimeter wavelength domain. The extensive site tests have documented the unique characteristics of this remote, high-altitude desert site. Clearly, it is a most promising site for the new telescope array, among the very best in the world. To protect the pristine environment of Chajnantor, the Chilean government has declared a large part of the area a scientific preserve. ALMA is expected to enter into operations incrementally from 2007, with all antennas being fully operational by 2012. When finished, it will become one of the most important observational tools worldwide, providing unprecedented access to space for a young and dynamic field of astrophysics. While we expect that ALMA will enable us to gain new insights into the birth of the first galaxies, as well as to the formation of stars and planets, it will have a major impact on virtually all fields of astronomical research, as it enables astronomers to investigate and understand the underlying physical processes behind the phenomena they see in the sky. But we should not be surprised if ALMA gives rise to completely unexpected discoveries, similar to when Karl Jansky pointed his antenna to the sky for the first time.